This section explains the origin and trajectory of microfluidics as a single structural move. Microfluidics is MEMS turned onto fluids, the same miniaturization move that shrank sensors into every phone now applied to submicroliter liquid handling. The payoff is the lab on chip, a wet lab collapsed onto one substrate. The chapter's arc reads as a chain of substrate substitutions, where each new material removes the binding constraint the prior one imposed. Silicon, opaque and costly, gives way to glass and PDMS, which are transparent, cheap, and soft. Lithographable. Those in turn give way to paper, which is disposable, self-wicking, and needs no pump. Integration climbs in parallel. First come isolated components, the pumps, mixers, and valves. Then come complex integrated systems. Then come application-oriented ones. To predict any instance, name the constraint the current substrate imposes on optical readout, cost, or fluid actuation. The next material is whatever relaxes it. This section explains why microfluidics behaves nothing like the macro scale. And it all follows from one fact about scaling. Shrink a channel and the force hierarchy inverts. Each force scales with length by its own exponent. Inertia and gravity scale as volume, meaning as the cube of length. Viscosity and surface tension scale as surface, meaning as length, or as length squared. So at the micron, the surface terms swung the bulk. Once the macron, the surface terms swung the bulk. Once the macro scale taught you to trust. The chapter is one corollary chain from that single fact. Viscous over inertial gives a vanishing Reynolds number, hence laminar flow, hence transport by diffusion rather than convection, hence capillarity and interfaces ruling the device. Hold the scaling exponents and you regenerate every downstream result yourself. One boundary keeps it honest. This holds only above the molecular mean-free path, where the fluid stays continuous. Below that scale, the continuum law dies and quantum thermodynamics takes over. This section explains how microfluidic devices are fabricated and why their surfaces must be modified. The chapter reads, Device Making as a Constraint. Satisfaction problem. You do not pick a fabrication process. You pin the application's demands, optical transparency, solvent resistance, channel geometry, disposable cost. Then the material that satisfies those demands dictates its own process. Silicon inherits integrated circuit etching, PDMS integrated circuit. Etching PDMS integrated circuit etching. PDMS invites casting, thermi-aquils, varsuses, Alsent a one-ane. Then comes the inversion that makes the whole chapter turn. Shrink the channel and the surface to volume ratio explodes. So the bulk material stops governing behavior and the surface takes over. Wettability and adhesion become the leading term of function. That is why a second independent step exists at all. Fabrication sets the geometry. Surface modification tunes the variable that the microscale amplifies. Predict any new device by asking which constraint binds, then which surface it exposes. This section explains why microfluidics needs simulation at all, and how to choose the right simulation method. Simulation earns its place where experiment goes blind and theory stalls. That place is the low Reynolds microscale, where surface tension and diffusion outrank inertia and no closed form survives. The spine of the chapter is one choice, repeated. At what grain do you resolve matter? Picture a ladder. On the finest rung, molecular dynamics and DSMC track individual particles under Newton's law. On the middle rung, dissipative, particle dynamics and lattice. Boltzmann, coarsened to ensembles. On the coarsest rung, continuum, methods, ensembles. On the coarsest rung, continuum, methods, and CFD solve the Navier-Stokes equations over fields. Each rung trades compute for resolution. The dominant physics at your length scale fixes which rung you stand on. Software is just each rung made executable. The generative move is this: pick the method by where the physics you need lives on the atomistic to continuum axis. This section explains the structural primitive behind digital microfluidics. A continuous microfluidic chip freezes its plumbing at fabrication. The channels are the program, etched once, unreroutable. Digital microfluidics inverts that. Strip the channels, tile the surface with an addressable electrode grid, and move discrete droplets by switching voltages cell to cell. The flow path stops being geometry and becomes runtime software. Any route is reprogrammable, many droplets are steered independently, and no pumps or valves are moving. That is the same leap as fixed function circuitry to the stored program machine. A droplet is a bit, an electrode is a cell, and transport, merge, split, and electrode is a cell, and transport, merge, split, and dispense are the instruction set. The whole chapter's arc is this one substitution, the hardware path replaced by programmable addressing. Every configuration and technique that follows is its consequence. This section explains what chemical analysis means on a microfluidic chip. Here, the phrase narrows immediately and without apology to one thing: electrochemistry on a chip. The primitive to carry forward is this: a microchannel electrode is a quantitative instrument only because laminar, low Reynolds number flow makes mass transport to the electrode exactly solvable. So, the measured Faradaic current becomes a forward model of the flow rate. Invert it against finite element or boundary element theory, and you recover concentration and reaction kinetics. Microfluidics keeps the electrochemistry unchanged. What it does is shrink the century-old hydrodynamic electrode tradition, the rotating disk, the channel flow cell, onto fabricable geometry. The shrink pays off because computable flow buys you calibration-free numbers. Everything downstream is this same move. Read through a different applied potential, voltammetry, amperometry, potentiometry, conductometry. This section explains the shared logic behind every microfluidic device for isolating circulating tumor cells. Every device here is one move. You pick a coordinate in which the rare tumor cell differs from the billion-fold denser blood. Then you shape flow that converts that difference into position. The whole catalog forks exactly once by what the coordinate is. Affinity methods read a molecular label, the ETCAM antibody laid on microposts, herringbones, or nanosurfaces. Here, chemistry does the sorting and geometry only maximizes contact. Known affinity methods read a physical scalar instead, size, deformability, or dielectric response. So inertial spirals, vortices, DEP, and acoustic waves push the larger or stiffer cells onto a predictable streamline with no label at all. You can predict any new device by asking two questions. Which observable does it separate on, and which force writes that observable into space? Capture yield, purity, and cell viability are simply where that one choice lands. This section explains the structural primitive behind microfluidics for disease diagnosis. Shrink the whole assay. Capture, separation, detection into one channel. Geometry and the biomarker is driven to U. A high surface-to-volume ratio and short diffusion paths push detection limits into the femtogram range, while sample to answer time collapses under 30 minutes. One move, applied 3 times, to proteins, to nucleic acids, to cells. Each is the same miniaturized pipeline pointed at a different denotation floating in blood or urine. Its place in the book is the payoff chapter. The generic advantages built earlier become clinical leverage exactly where sample volume and speed are the constraint. Everything else answers to. The boundary it keeps striking is this. A bulk chip reports only the population average, erasing cell-to-cell heterogeneity. That erasure is what forces the eventual descent to single-cell resolution. This section explains why gene expression is measured on a microfluidic device. Bulk gene expression assays report a median. They average over thousands of cells and drown the very heterogeneity, embryonic, immune, tumor, initiating, that carries the biology. The obstruction is concentration. The mRNA copies are few, the transcription factors fewer, and as single cells molecules sit below the detection floor once they are diluted into a lab-scale volume. The microfluidic move is the whole chapter compressed to one lever. Shrink the reaction from microliters to pico and nanoliters, and the same scarce molecules occupy a volume 1,000-fold smaller, so their effective concentration clears the floor. Confinement is amplification. Everything downstream, on-chip PCR, fish, digital counting is that one primitive spent on a different readout. This section explains why shrinking an organic synthesis reactor to a micron-wide channel inverts every liability of a batch vessel. The reason is that transport scales against length. When you make the bore small, the physics that governs mixing, heat, and safety all move in your favor at once. Start with diffusion. Diffusion time falls as the square of the length, so mixing drops from minutes to milliseconds. Surface-to-volume ratio rises as 1 over the length, so heat exchange runs at something like 10,000 to 50,000 square meters per cubic meter against a bulk vessel's 100 square meters per cubic meter. That means the channel can shed heat faster than any exotherm the reaction. Flow adds the next gift, laminar. Oriented flow makes residence time deterministic, so the reaction becomes a position along the channel rather than a duration in a pot. A tiny reacting volume disarms explosive or runaway chemistry, and you reach scale by numbering up identical channels rather than redesigning a single one. The chapter's thesis is this: continuous flow. Organic synthesis is what emerges once the geometry rather than the chemistry sets the rate-limiting term. This section explains why a polymeric microparticle is best understood as a frozen emulsion. A polymeric microparticle is a frozen emulsion. Solidify the droplet and every liquid interface it carried becomes a permanent material boundary. That one move splits the chapter's whole control problem into 2 orthogonal knobs. The first knob is hydrodynamics, the flow regime of dripping, jetting, and co-flowing governed by the capillary number. It sets size and monodispersity. The second knob is interfacial thermodynamics, phase separation, and spreading coefficients. It sets internal architecture, core shell, Janus, multi-compartment. Complexity here is compositional. Nest, an emulsion inside, an emulsion and you nest, structure inside structure. So simple to complex counts only how many interfaces you template before freezing. You never sculpt the particle. You shape the fluid and stop time. Geometry comes from kinetics, topology from thermodynamics. This section explains why the synthesis of magnetic nanomaterials becomes a geometry problem once you shrink the reactor. The whole chapter is one move: make the vessel small enough that the geometry of the vessel sets the product, while the chemistry stops being what decides the outcome. Magnetic nanoparticles want monodispersity, and monodispersity is a residence time problem. Every particle should experience the same time, the same temperature, and the same mixing. A single-phase laminar stream fails this. Its flow has a parabolic profile, the Poisson profile, which spreads the residence times across the particles. This spreading is called Taylor-Harris dispersion, and because of it, the size distribution smears. The fix is to stop treating the channel as one reactor. Cut the flow into immiscible droplets. Each droplet is an identical closed vessel with its own narrowed, near-discrete residence time. It is the same co-precipitation of iron 2 and iron 3 that runs in a beaker, but now the distribution collapses because transport is geometrically pinned. Continuous flow versus droplet. Segmented is the one axis that everything else hangs from. This section explains how microfluidic synthesis turns nanocrystal formation into a scheduled process, and why that gives control that batch chemistry cannot. Batch chemistry hands the whole reaction one set of conditions and waits. The microfluidic channel instead makes position along the flow into time, so every stage of nanocrystal formation, mix, nucleate, grow, ripen, quench, becomes an addressable coordinate that you tune independently by flow rate and channel geometry. That is the chapter's whole move. The reactor stops being a pot and becomes a written schedule of kinetic parameters laid out in space. The payoff is control where thermodynamics gives none. The 3 cobalt phases sit near isoenergetic, so a bottle cannot pick between them. Yet flow velocity alone selects the FCC phase, the HCP phase, or the epsilon phase. And you grow output by paralleling identical channels, scaling out, never by enlarging one vessel. This section explains why making a composite well reduces to controlling time, and how a microfluidic channel gives you that control. A composite's function lives in its interfaces, and interfaces are fixed at the moment of formation. So controlling the material reduces to controlling the timeline along which solute nucleates, grows, and aggregates. Lemire's 4 stages are a temporal sequence. A batch reactor superimposes them, with every droplet living a different history. The chapter's single move is to lay that timeline onto a channel. Residence time equals geometry times flow rate, so position along the flow becomes reaction stage. Nucleate here, grow there, terminate before aggregation blocks the channel. A temporal sequence made spatial is one made addressable. Each stage now tunes independently. From this you predict the rest. Any staged kinetics a beaker will not let you separate. You separate by giving it length. This part explains how microfluidic synthesis controls where and when a metal-organic framework crystallizes. A microfluidic reactor is a machine for controlling where and when a reaction happens, and MOF crystallization is exquisitely sensitive to exactly that. Bulk synthesis dumps metal ions and organic linkers together. Nucleation and growth overlap chaotically, so crystal size scatters. Squeeze the same reaction into a micron-scale channel or a droplet, and you buy 2 levers that batch chemistry cannot. The first is millisecond uniform mixing. The second is a residence time you dial by flow rate. Nucleation decouples from growth. Every crystal sees the same history, so it emerges the same size. The membrane case is the same move projected onto a surface. Confine the reaction to a laminar interface and the moth grows as a continuous, defect-controlled film. The primitive is this: govern the reaction space-time coordinates, and you govern the crystal. This closing section names the basis the whole book was implicitly written in. A closing chapter's real job is exactly that. Every device across the prior 16 chapters resolves to a single point in one small product space. That space has 3 axes multiplied together. The first is flow type, which is continuous, droplet, segmented, or spray. The second is driving force, which is body, electrokinetic, magnetic, optical, capillary, and their couplings. The third is construction material. A device is a choice of one coordinate on each of these 3. There is no new physics here. The perspective is that the field advances by extending each axis independently and by interfusing with adjacent disciplines. It does not advance by discovering new principles. So here is the compression to carry forward. Microfluidics is miniaturization made modular. Pick a coordinate on each cornerstone and you have specified a device. The frontier is the axes lengthening rather than the axes multiplying.